It's a pleasure to be here. I very much thank the organizing committee for inviting me. It's my first time in Serbia and been absolutely delightful. What I'm going to be doing is talking about the current situation of where we are now and how we got there, looking at issues much like the chap that was presenting regarding Iran. I will be using primarily case studies from India and Zambezi, the Zambezi River, not the Zambezi country, because there isn't one. Sorry about that. And then subsequently talking about climate change specifically as it applies to Bangladesh. So the emphasis is very much on developing world. It is also to a large extent related to the social aspects as well. And again, referring back to the previous speaker on Iran, because the social impacts will be quite apparent is very, very important. And then finally, some conclusions. This is pretty much background and pretty obvious, but I think it's useful to go through some quick comments on significant challenges because of the growth in groundwater withdrawals that have occurred over the last 40 years. UNESCO in 2003 provided some estimates. 50% of the potable water supplies, 40% of the demand for industry, and 20% of the irrigation needs are supplied by groundwater. So obviously a huge influence. And clearly, everyone here is pretty much aware of the fact that the local availability, the reliability, more or less, during drought, and typically not requiring much treatment is highly relevant. It is then useful to look at this figure, or this table, which refers to the extent and magnitude of the global groundwater revolution. And I'm going to be referring periodically to India, Pakistan, Punjab, and to a lesser extent some other countries as we go through it. But the magnitude of these numbers is substantial, as we'll see. And the other dimension which I really want to refer to is the last column, which refers to the percentage of the population dependent on the groundwater. 55 to 60% in India, 60 to 65% in Pakistan, and so on. Huge numbers, huge social implication, as we will see as we proceed. The net result is, because of groundwater withdrawals having been increased in the 1950 period, the estimates were approximately 100 to 150 cubic kilometers per year. They are now at the range of 950 to 1,000. The problem obviously is, to what degree is this sustainable? And this is obviously very much a worldwide generalization, but only approximately 2% of the precipitation infiltrates to the groundwater. And clearly that's not uniform, but it's very important that there is a finite amount of water that is available. This figure, referenced down here, but what is interesting is to look at a series of these countries, and India, I'm going to skip the United States because it's obviously quite different in many respects, but India, China, Pakistan, Iran, and Bangladesh. In particular, those ones. What we see over here is the area under groundwater irrigation. So if we look at India, it's about 26 million hectares of land that's irrigated by groundwater irrigation. We drop down here to China, to Pakistan, to Iran, and we get to Bangladesh, and the number really isn't very large. But of course, Bangladesh is not a very big country. So if we look instead over here on the right-hand axis, this is the share of the farming area under groundwater irrigation. So Bangladesh, albeit the number is only about 2.5, but the actual area of farming under groundwater irrigation is very substantial. It's of the order of 30%. So over here on the right. So clearly groundwater irrigation is huge. And this is what I was referring to a few minutes ago. This is 1940 to 1950 up to more or less the present time. And it's showing the groundwater withdrawal rates in cubic kilometers per year for individual countries. The rate of change of some of those is profound, to say the least. This is obviously the rural electrification, the availability of the oil-fired engines to bring the water to the surface, and so on. But the trends are really, really important, and I think I'm running out of juice on my pointer, but anyway, taking a look at those huge numbers and at a very substantial escalation rate. Now we look at the next one, and this is now the long-term average groundwater recharge, and the circles there indicate areas that are intensively groundwater use for agriculture. Southwest United States, no big surprise, and a series of others. The Iranian reference is right here. The color designation is up here, but there really shouldn't be too many surprises. A couple things, however, to note. First of all, I will be referring to it later, but this is the Zambezi River in Africa, so in the southern portion of the continent. In India, which I'll refer to later also quite frequently, but is on the west versus the east of the country, very significant amounts of recharge difference. This will be very important too in terms of how much irrigation can you actually sustain in those areas. And the third area of particular interest is here in China, where the south has lots of water, the north has very little water. So on average, it's fine, but the regional disparity is huge. So this is a high recharge in the south, but not in the north. This is recharge is less in the west than the east. This is the Zambezi, and minimal recharge in the U.S., southwest, and minimal recharge in Iran. This is the reason why, in part, the irrigation has changed so much. This is the growth of irrigation pumps in India, and it shows oil engines and electric pumps as a function of time. So from the rural electrification, from the oil-powered engines, the ability to bring the water to the surface has changed profoundly in the last 40 years. Talking about then a quick reference to India, it has the highest groundwater usage in the world. It had 1 million tube wells in 1960. It has 19 million tube wells now, well, more than that now. It has 45% of its irrigation requirements served by groundwater, and 67% of the people in India are farmers. If you're a politician, one of the ways that you will keep people happy is to provide water. This will be a problem. So increased energy needs as a result of having to pump. First of all, just simply pumping the water anyway, but then also with water decline through overpumping, increased energy requirement. Water quality concerns and subsidence are consequent measure impacts as well. And this is a picture, obviously, primarily of India, and you can see here the headwaters of the Indus River, which feeds Pakistan, but this is in India, and they are thinking of diverting the water down into the dry areas of Rajasthan, Gujarat, and so on. Similarly, here's the Ganges River, which ultimately flows down to Bangladesh, which again I will refer to later, but here's Calcutta down here with 20 million plus people, very short on water. So they are already, through the Farakka barrage, diverting water. The intent is to divert even more water as they move into the future. So when we think of Bangladesh in a few minutes, think of its position. It is a delta. It receives huge amounts of water, in fact, enormous amounts of flooding from the Ganges and also from the Brahmaputra up here. And China is thinking of moving that water to the north as opposed to allowing it to continue to travel south. So the water diversion is going to be something that I'll be referring to. So relevant considerations in terms of India is they have, in some cases, flat rate billing, and in some cases they have free electricity if you're going to use it for agriculture. So the cost of metering, just to put a few examples in context, the cost of metering was 40% of the cost of electricity. Huge power subsidies then to the farmer. It makes them very happy because they now have water, much like the Iranian example of the 800 grams per cubic meter applied. The electricity for use in Tamil Nadu, which is one of the southern states, is actually free if you're using it for agriculture. Well, what happens then is the power companies are going bankrupt. And 27 to 54% of the energy in those southern states is now used for agriculture. As a result, you've got significant overpumping, causing the aquifers to drop by 1 to 3 meters annually. In Karnataka, again one of the southern states, approximately 20% of the 2.3 million tube wells are going dry every year, having to be re-drilled and so on, and obviously more electricity involved in pumping the water to the surface. These are the groundwater level maps in India, and the very intensive colors up here are in the Rajasthan, Gujarat, and so on areas, and those are 40 meters, some of them that are deep and declining rapidly. Similarly also here, if you recall, there wasn't much recharge. The groundwater levels are not so high, but they cannot get much more water out. So when we then look at here, year 2001 up to 2025, This is the country's expected population as they proceed into the future. They will pass China in another 10 or so years. The projected groundwater usage per year, if you look at this column, is more or less constant, 246, 248, 251, and so on, 259. But that's the total. When you look at it on a per capita basis, the last column, you see that actually it's dropping significantly. That's because there simply is not enough water available. Now let's switch to the second example that I was referring to. This is the Zambezi River in southern Africa. There, the drainage shed for the Zambezi River is indicated in the lighter color. It drains 8 countries: Angola, Zambia, Malawi, Zimbabwe, Botswana, etc. And these are the 8 countries here indicated. And what I did just to try to put this into context is looking over here. This is the per capita water available in the year 2002 for each of those 8 countries. The only one that's actually under water stress in 2002 is Malawi. The others are in reasonable shape. They have sufficient water. But now let's look at that same context, the same 8 countries. Here's the population in 1995. Here's the average growth rate in terms of population expected. And ultimately then in 2050, these are the populations expected. The magnitudes aren't particularly relevant, but what is relevant is what happens to the water availability per person. Here we are in 2020, and here we are in 2050 over here on the right. And because of the population growth, you see dramatic declines. This is nothing to do with climate change. This is simply population growth. And if we look at the scale here, this is the area, this white line is an area of water stress. The area of the black is severe water shortage. Now what we're seeing is very rapidly a series of countries are getting into the periods or areas of severe water stress, not by climate change, but simply by population, because there is simply not enough water available. So, just a little bit of background. Now let's talk a little bit more about climate change. Now what I have depicted here is Bangladesh. So here's Bangladesh. India would be to the west, China to the north, and so on. And the size of the circles are all that's relevant here, but they show the percentage of groundwater irrigation. So large diameter means more irrigation from the groundwater. There's very little in the coastal region, because if you try to irrigate very much by groundwater pumping, you get saline intrusion, and that simply won't work. What is relevant, though, is up here, in particular, if you remember my reference to the Ganges River, it comes in right here. Huge amounts of groundwater utilization for irrigation, 160 million people, one of the most densely populated countries in the world. Now if we look at the groundwater levels in terms of just different months, the intense colors, and I'm colorblind, but I'm pretty sure that's brown, this is for 1 month versus another month. What this is, just to put it in context, up in the top right where the legend is, shows that it's very, very deep. It's about 40 meters deep down to the groundwater. These areas here, there is some fluctuation from one season to another, but not dramatic. In other words, they are sustained. But of course, they have the given precipitation levels. They have the inflow from the Ganges and the Brahmaputra, and obviously a lot of people, but a lot of groundwater irrigation. Now let's look to see what climate change implications are. This is 1950. This is the present time up here on the right. The top line is their summer temperature, and the average temperature is this one, and the winter temperature is here. This is definitely not Canada, for those who've been there. 15 to 20 degrees, whatever. In the winter, we would love that, but regardless. It's clear that there is a significant slope to those lines. The temperatures are increasing. They have over a 50-year period. So what's happening in the future? This is that same historical period here, that 50-year period. These are projections into the future. What we did was we ran 4 computer models for future climate change scenarios. And this is annual temperatures then, projected into the future. So all of the models, at least to the year of 2050, are showing similar kinds of ramification. In other words, similar magnitudes of increase in temperature. As we get out to the further and further to the right, to the more distant periods, there's more deviation. But let's just look to the year 2050. So far, what we're seeing is temperatures are expected to increase. This is now precipitation, and I didn't show you the previous one, but this is the historical precipitation, also increasing. Good, we're going to get more water. And actually, when we run then those same computer models, these are the ones referred to up here, up to the year 2050, the answers are quite comparable from one to another, showing a continuing increase. A good, more water, because it's going to be hotter there. The problem is, when's that water going to happen? This is January through December. These are the temperature changes, which are not relevant, particularly for my discussion right now, but what the last column is the ratio of the precipitation in the year 2100 to the year 2000. And what's disturbing is, look how many of them are less than 1, and then there's one that's also quite different, and then, again, less than 1. So yes, the models are suggesting there's going to be more precipitation, but when it's wet, if you look at the size of this magnitude here, 431 becomes 542. When it's wet, it's going to be more wet. So is that water really going to be useful? Not necessarily, because it will rain more intensively when it rains. This is a serious implication. So this is suggesting that, yes, increased water, that's helpful, but it's not going to come. Bangladesh is 29 feet on average elevation. Incredibly flat area. It's the greatest place in the world to ride a bicycle because there are no hills. But it also means that they get flooded. And so flooding is a huge issue. It's going to perhaps intensify. Clearly it's a function of what India and China do with the water in the Ganges and the Brahmaputra. But anyway, this is now a potential evapotranspiration. So again, the historical period, we didn't have as long a record, but this is the historical period. These are the projections into the future. Again, reasonable similarity in the projections from the various climate change models. So, what are the implications of climate change? Well, we are expecting to see increased precipitation. And this is a very simplified view of the world, but the precipitation increase projected to 2050 is about 14%. The evapotranspiration projected, this was the Thornthwaite model used to project the evapotranspiration, was going to increase about 13%. So it's, similar. But unfortunately, not all the precipitation will be available due to intensity issues. So actually, it's going to hurt. They're going to have less water available. They are currently using groundwater extensively for irrigation. The country of India is already diverting water down, and the intent is to exaggerate or increase that down to Calcutta because of the needs of the water there, which means then they will not have that same recharge during the flooding period. This is not good news. So this is a problem. If this water is sent down here, no longer ends up in Bangladesh, they will get more precip, but it won't be useful precip, or at least not as useful as you might otherwise expect. So annual averages are dangerous. The result is likely to be bigger problems. This is taken from an IFPRI 2002 report, but it basically is comparable to what I've been suggesting here. The dark or black is sustainable yield for China, India, and other areas. This is the 1995 extraction rate. This is the projected for 2025. That's not sustainable. India is already beyond sustainability. It's going to get worse. And the others, obviously, but I'm not really addressing those right now. And finally, just as one kind of quick example, but just to suggest this is not a problem unique to India or Bangladesh or the Zambezi. This is China. Here's Beijing up here. Here's Tianjin. And if you read these portions down here on the bottom right, I can't read it off the screen, but I'll read them here. The gray tone is area with 40 meter plus decline in bathymetric surface of deep confined freshwater aquifer since 1960. And the crosshatched area there is with 20 plus meters. So this is not a problem unique to the countries I referred to. It is unfortunately a rather pervasive issue. And I'll skip that one. So I think I'm just about right on time. Groundwater exploitation has been enormously important to where we are today. No question about it. It has provided foodstuffs that we would not otherwise have available. The population growth has enormous implications, and I just depicted it by the Zambezi the 8 countries, but it's not a unique situation. Actually, it's more important. I've done the comparable analyses for the Zambezi in terms of climate change, etc., and the population is the important one. Climate change is really not as important. Water diversions will increase, and hence less recharge will occur, and that is in all likelihood. India is definitely going to move to divert water, but Turkey is already doing it from the Euphrates and the Tigris. Iraq will have less water. Chinese are doing it in Mekong, which means Cambodians are wondering, where did all the water go? Because Mekong simply no longer carries as much water, and so on. And I won't, I know it's pretty safe in this audience, but we have in Canada this large neighbor to the south. We refer to it as like sleeping with an elephant, where they are looking very thirstily at the Great Lakes. We'll discuss that later. Anyway, climate change scenarios, in many cases, it looks like there would be more precipitation, but when it rains, it's going to rain more intensively, and when there is more intensive rain, the infiltration opportunity is not necessarily expanded commensurate with that additional rainfall. So the security of groundwater is a major concern for the future, and it's not unique to one country. I think that's it. I'm sorry, it's not it. The most important part is to acknowledge the people that did all the hard work. University of Guelph is a fairly well-known, or well-kept secret, I should say. We are actually the most research-intensive university in Canada, and whenever I'm outside Canada, I say I come from Toronto because people know where Toronto is. But basically, it's just 50 miles west of, or 80 kilometers west of Toronto. And I have the pleasure of working with a large number of very fine people. In particular, I owe thanks to Joe Brunsting, Andy DeYoung, and Emma Thompson, who are graduate students who did the hard work, and to the Canada Research Chairs Program, which provides the money for them. Thank you.